All right, let's dive into something that can literally make or break incredibly expensive machinery, but it's almost always overlooked. We're talking about the tiny, tiny threads that hold everything together.
You can have a hydraulic part that's machined to absolute perfection, right? Every dimension is spot on, but just one single, seemingly insignificant threaded port can become the weak link that brings the whole system crashing down. It's a perfect example of how the smallest detail can have the biggest, most catastrophic impact.
And this is really where our story begins. Just picture it, this powerful, complex piece of machinery, and it's all running under immense pressure. Everything looks great until a tiny little leak starts. And that leak, well, it traces all the way back to one faulty thread. And from there, you get loss of pressure, contamination, and boom, critical system failure. So, our investigation really kicks off right here, basically at the scene of the crime. We're going to figure out exactly why these failures happen by looking deep inside the very connections that are supposed to hold these incredibly powerful systems together. The thing is, the evidence is almost always microscopic. The clues aren't big and obvious, no, they're hidden. We're talking about poor thread finishes that cause leaks, or fittings that completely seize up when you're trying to assemble them, or even these tiny hidden metal burrs that are just waiting for the right moment to break free and wreak havoc on the entire system. Okay, so to really get what's going on, we need to meet the main characters in our story, and I'm talking about the materials themselves. Let's take a look at the different types of stainless steel we're dealing with here. Right off the bat, you have to understand that not all stainless steel is created equal. Not even close. Each alloy has its own unique personality, and it reacts to the intense pressure and friction of being threaded in totally different ways. So, knowing your material, that's step one in preventing a disaster. Now, this is where it gets really interesting, because this table basically lays out our prime suspects. You've got 303 stainless, which, okay, it's pretty easy to machine, so that's a plus. Then your 316. It's amazing when it comes to corrosion resistance, but it has this nasty habit of smearing when you cut it. And then there's the big one, 17-4pH. It's unbelievably strong, but it is a real beast to work with, especially after it's been hardened. Each one presents a totally unique challenge. All right, now that we know the materials, let's go ahead and identify the specific villains, the actual culprits that cause our threads to fail. So first up is our main bad guy, thread galling. This is a really nasty thing that happens where two stainless steel surfaces basically fuse themselves together under pressure. So as you're tightening a fitting, the threads literally start to tear and weld to each other until the whole thing just locks up solid. So what's actually causing this? Well, it's basically a chain reaction. You see these microscopic high points on rougher thread surfaces? They create intense friction and a ton of heat as you tighten things. That heat is actually enough to cause the metal surfaces to weld together. And once that happens, the connection is ruined. A really smooth thread surface is your best first line of defense against this. Our next enemy is a lot smaller, way quieter, but honestly, it's just as destructive. It's the burr. This is a tiny, razor-sharp little piece of metal that gets left behind from the machining process. It might not look like much, but trust me, inside a hydraulic system, it's a ticking time bomb. Just look at this trail of destruction. A little burr forms on the edge of a thread. Then, later on, under all that hydraulic pressure, it breaks loose and starts traveling through the system like a tiny little missile. It can easily get stuck in a sensitive valve or scratch a critical sealing surface. And that's all it takes to cause internal leaks and total system failure. And our third enemy is something called pitch diameter variation. This one's a bit more subtle. Imagine trying to screw a cap on a water bottle, but the threads are all wavy instead of straight. It would feel tight, then loose, then tight again, right? You'd never get a perfect seal. That is exactly what's happening here, and it makes the connection completely unreliable when it's under pressure. So what's going on here is that the material itself is literally fighting back. The insane pressure you need to cut stainless steel can cause the cutting tool to bend ever so slightly, and that changes the thread's shape. On top of that, the material work hardens, which means it actually gets tougher with every pass of the tool, which makes it even harder to maintain accuracy. So we've identified the enemies. Now let's look at the two main methods people use to create threads in the first place and see how they really stack up in this fight for quality. So, on one side, you've got tapping. It's fast, sure, but it's risky. It really struggles to get those little metal chips out of deep holes, and those chips can completely ruin the thread on their way out. Then, on the other side, you have thread milling. It's way more controlled, it's much better at getting chips out, and it lets you make these tiny, precise adjustments. And in these high-stakes applications, that control, it's everything.
So we've profiled the materials, we've identified the enemies, and we've compared the methods. Now let's pull it all together and reveal the final piece of the puzzle, the secret to making perfect, reliable threads.
Believe it or not, the secret weapon, the thing that can defeat almost all of these enemies at the same time, is coolant. Yeah, proper coolant delivery isn't just some minor detail. It is the single most important factor in creating a high-quality thread. See, coolant does a lot more than just cool. It lubricates the cut, which reduces the friction that leads to galling. It forcefully flushes away all those chips and burrs before they can do any damage. And by keeping the temperature stable, it helps prevent the tool from bending, which ensures you get a consistent thread. But here's the catch. For it to work, it has to be high pressure, and it has to be aimed perfectly at the cutting edge. And really, this quote from the source material just sums it all up perfectly. It's not any one thing. Success comes from a combination of having the right tools, controlling the cutting conditions, and, critically, having superior coolant delivery. You get those three things right, and you get a perfect thread. So the ultimate takeaway here is pretty simple. When you're talking about high-pressure hydraulic systems, the quality of a thread is never, ever just a small detail. It's the absolute foundation that the reliability, the safety, and the performance of the entire system is built on. And that kind of leaves us with one final thought, right? The biggest, most complex, most powerful systems in the world all depend on getting the very smallest details right. So the real question is, which ones are you overlooking?